It's a great honour for me to be asked to say a few words about Blackett on this historic occasion. Blackett was undoubtedly unique in many respects. He was unique in the fact that he was never intended to be a scientist. He was destined for a naval career and was at Dartmouth, not having finished his training when war broke out in 1914. Then, to a great extent, he was fortunate because he was posted to H.M.S. Carnarvon as a midshipman, but was late in arriving, and instead sailed on Monmouth. Now, shortly afterwards, Monmouth was sunk by the German battleships with all lives, but by that time Blackett had transferred to his original ship because they were both coaling the Cape Verde Islands. Well, that's by the way. He saw action, first of all, in the Battle of the Falkland Islands, and then, most remarkably, at the Great Battle of Jutland, when he was on the flagship of the 5th Battle Squadron, HMS Barham, and his diary of those days, I hope still exists. I had the great honor of reading it, and I must say that it is one of the most memorable pieces of writing that I've ever had the pleasure to read, or the agony to read. And he calculated that during the battle, about 300 12-inch ships were fired at Barham, but he survived, but many people did not survive that battle. He was later posted to the destroyer squadron, and in the latter years of the war, he became very dissatisfied with the accuracy of the gunnery of the Royal Navy. And he discovered it was far worse than that of the German gunners. But the squadron officer refused to take his advice, take any notice of his statistics, and this increased Blackett's dissatisfaction with the Navy. He determined to resign from the Navy at the end of the war, and in fact wrote both to the University of London and to the Naval Instrument Makers Bar and Stroud to inquire about possible occupations. In the event, other circumstances determined his career as a scientist. In January of 1919, the Admiralty decided to send the cadets whose course had been interrupted by the opening war back for a refresher course to Cambridge. And in January of 1919, Blackett arrived in naval uniform at Malden College. That was a great turning point. A few days later, he walked into the Cavendish laboratory to see what a scientific lab was like, and almost immediately became a student in the Cavendish, and with remarkable speed, I think in 2 years, got a first in physics. At the age of 24, 1923, he became a research student at Rutherford. Now, Rutherford, you will recall, had recently left Manchester, where he had succeeded in disintegrating the nitrogen nucleus by firing alpha particles at it from radioactive substances. And he was anxious to obtain a visual picture of this event. There had been a Japanese student, Shmitsu, who had started this work with a Wilson expansion chamber. And, but Shmitsu had returned to Japan after taking a few thousand photographs. And Rutherford told Blackett to continue work with this chamber and try to obtain the visual picture of the disintegration. Blackett, of course, as you will have realized, was a master at technique and technological work. And he began the first of his major modifications of this cloud chamber to make it automatic. He had calculated that he would need to make a few million exposures in order to observe a few disintegrations. In fact, in the first 24,000 expansions which he analyzed, he discovered this most beautiful photograph, which at least in the 1930s adorned every textbook of physics in this country, where you saw the track of the alpha particle and the recoil oxygen nucleus and the proton, a most beautiful photograph. He then decided, much to Rutherford's annoyance, to take a year's leave and go to Germany to study with Frank, to study the electronic structure of the atom. This annoyed Rutherford that anybody should wish to leave the Cavendish, and secondly, that anyone should think of studying the outside of the atom instead of the nucleus. Anyhow, Blackett returned after a year and continued his nuclear work. Then in 1932, Occhialini arrived from Italy, bringing with him the coincidence counting system using Geiger counters devised by Bruno Rossi. And Blackett, of course, immediately saw the possibility of adopting this coincidence system to take photographs in a cloud chamber. And with a lead plate across the cloud chamber, he used the coincidence system to take photographs of cosmic ray particles entering the chamber and the showers emerging from the lead plate. He placed the chamber in a magnetic field so that from the curvature he could measure the energy of the particles. And it is typical of Blackett's ingenuity that instead of trying to measure the actual curvature, which was very small and very difficult, he devised an achromatic prism so that he only had to judge the straightness of the track and not the curvature. And by having calibrated that, he was able to obtain quite reasonably accurate measurements of the energy of the particles. Well, you know the result of this. It was a brilliant success. Those of you who were at the Royal Society Memorial meeting after Blackett's death may recall Occhialini's tribute and his vivid description of Blackett emerging from the dark room, holding up the plates, one on each. In the first, I think they were so successful that in the first 700 exposures, there were about 500 very good cosmic ray showers in these plates. And amongst these were the tracks which indicated that there were particles of electronic mass with a positive charge. And that was, as you will recall, the discovery of the positive electron, which had in fact been preempted by Anderson in the United States. Well, it was my good fortune to know Occhialini. As Blackett said, he came for 3 weeks and stayed for 3 years. But not Blackett. Blackett became increasingly dissatisfied. He apparently did not get on very well with Rutherford. I think part of the trouble was that Rutherford thought he wasn't doing enough teaching. He was concentrating too much on research, and of course that is exactly what Blackett wanted to do. So in 1933, he took the opportunity of accepting the chair at Birkbeck College, where the teaching was then at night, and he had all day to carry out his research. He decided to build a much bigger cosmic ray chamber and a much bigger magnet to study the energy spectrum of the primary cosmic ray particles. He obtained a grant of something over £1,000 from the Mon Fund of the Royal Society, and I don't know exactly the increase of the cost, but that was a very considerable sum of money in those days. And he had permission to build this equipment in Mallet Street, I think, the famous Magnet House, if that's how you pronounce the name of the street, the Mallet Street in London, because of course there wasn't room at Birkbeck College. With this equipment, he and J.G. Wilson and Broad, who was visiting from America, extended the known limits of the energy spectrum of the primary cosmic rays. And then the troubles began. And it's important to remember that although Blackett was exceedingly brilliant, he was not always immediately right. And he was wrong for quite a few years on that occasion. The difficulty was that they had managed to extend their measurements to an energy from about an energy of 10 to the 5, 10 to the 6 electron volts to something in the order of 10 to the 10, 10 to the 12. And there still seemed to be primary particles of that energy reaching the ground. Now, on any scheme of classical physics, the radiation loss of an electron would make that impossible. And Blackett Blackett maintained that the quantum theory was failing at these high energies. Now, that was the occasion when I became involved myself with Blackett, because at that critical time he came to Manchester. Bragg had gone to the National Physical Laboratory. I know after a year he went to the Cavendish. Blackett succeeded him, bringing with him this massive 10-ton electromagnet, which was re-erected in the physics department in Manchester. And of course, in those days, the refugees from Europe, from Nazi Germany and Italy, were beginning to pour out of the country, and a vast majority of them came to Blackett. He was so well known, they either came to stay or came for a few days. And on one weekend, we had Heisenberg, who of course was a good Nazi and eventually returned to Germany, Heisenberg and Barber. And it was on that occasion, a memorable occasion, when Blackett was convinced that that the quantum theory was correct at high energies, and that we were dealing with a new particle, then the so-called heavy electron, we used to call them the mesotron, believed at that time to be the particle which Yukawa had predicted in 1935. As a matter of fact, we now know it's not the case. The particle is a different mass than that. Well, Blackett, of course, in Manchester began the tremendous expansion of the cosmic ray work, in which many of us were privileged to take place, not only those of us who were English, but those of us who were from Europe, and it was a most memorable year. But Blackett became increasingly distracted. I often wondered why he was away from the laboratory so much. He would return with putting a card out of his pocket with an enormous list of jobs which we ought to have done or we should do. And he assumed that we all had his tremendous scientific and technical capability, making a Geiger counter from nothing or shifting a ton of lead blocks on top of an expansion chamber. Then it was not until early August of 1939 that we realized what was happening. Nowadays it's very difficult to remember the tremendous secrecy of those days. I was about to start a drive through Paris, picking up Pierre Auger in Paris, drive through Europe, to carry out some work on the Peak meeting. And I had a telephone call from Blackett, an urgent telephone call, saying, on no account you to start your journey across Europe. We have another job for you. And then, of course, you will now know what the situation is, that for the previous 4 years, since 1935, Blackett had been a critical member of the committee under Sir Henry Tizard, dealing with the problem of defense of the country against enemy bombers. And it was primarily because of that committee that the radar was favored as a possible means of detecting many aircraft, and the great coastal chain, CH chain, was erected along the east and south coasts of the British Isles, which played such a vital matter in the Great Battle of Britain, enabling our few scarce Spitfire and Hurricane squadrons to be retained on the ground until enemy raiders were really approaching this country. Unfortunately, the committee did not run smoothly. It was created on the advice of Wimperis and A.V. Hill by Lord Londonderry, the Secretary of State for Air. And he, when Churchill was already a considerable influence, and he persuaded Londonderry to appoint Lindemann, later Lord Cherwell, to this committee. And the disputes began immediately. Cherwell, I will refer to him as Cherwell, that's how we now remember him. Cherwell wanted more emphasis given to dropping parachute bombs in front of the enemy and infrared detection. Fortunately, he did not prevail. The meetings of this committee became so acrimonious that that the Tizard recommended they resign, which they did, and Londonderry reappointed the committee some months later without Charwell, but with Apperton and Merton as additional members. However, of course, as soon as Churchill was appointed First Lord of the Admiralty, he had Charwell as his scientific advisor, and the influence of the Tizard Committee rapidly declined. It was that event which led to the fact that at the beginning of the war, neither Blackett nor Tizard were exerting the enormous influence which they should have done on the technical and scientific developments to aid the Allies in their defense of England. Blackett, in fact, had very little to do in the first months of the war. And later in the autumn, he got an appointment as a principal scientific officer at the Royal Aircraft Establishment. He summoned Braddock, who'd been his associate at Birkbeck, and together they made the very famous Mark 14 bomb sight. Now, this was an amazing device, which they managed to devise an analog computer. Remember, no modern forms of computer in those days. They managed to devise an analog computer which would feed in the motions of the aircraft to such an extent that in a steep diving turn, the Mark 4 bomb sight could be used to bomb accurately. I think something like 40,000 of these bomb sights were fitted to the Royal Air Force machines, and it was also copied in America. But then, in August of 1940, General Pyle, who was the general commanding the anti-aircraft guns around London, came to a lecture with A.V. Hill, and he complained to A.V. Hill that he was not having much success in dealing with the German bombers who were attacking London. And Blackett had given him a lecture, presumably on the bomb site, and after the lecture, General Pyle said to Hill, "Why can't I have that chap Blackett?" And thereby began the amazing sequence which the rector referred to of the operational research. First of all, he worked with General Pyle, dealing with the analysis of the defense of London by the Ack guns, and I can't. There isn't time to go into all the details, but he for example, made an analysis. There weren't enough radars to equip more than half of the bombs of the Ack sites trying to defend London, and he made an analysis to show it was more important to use less sites and feed every lot of guns with the radar than encircling London. And he also discovered that the radar was feeding very poor data into the much more accurate bomb sites, visual bomb sites on the guns, and made a colossal improvement. I think the rounds per bird, as it was called, was reduced from 24,000 to a few thousand in a remarkably short space of time. He then, in 1941, went to Coastal Command and set up the operational research section in Coastal Command. He had been stolen, as General Pyle remarked, they have stolen my magician. He had been stolen by Joubert de la Ferté, who was then the Commander-in-Chief of Coastal Command. It was in Coastal Command that Blackett collected quite a brilliant team, E.J. Williams, Wallington, around him. And I think it's typical of the incredible insight that Blackett had, and the manner in which he always intuitively worked from first principles. We see the examples of this in Coastal Command. I just mentioned one. He was one night in the operations room of the Western Command in Liverpool, and on the wall was a map showing what was believed to be the distribution of the U-boats in the North Atlantic. And Blackett looked at this map with the statistics of the number of attacks we were making on the U-boats, and he decided that there was something terribly wrong between the estimated number of U-boats in the North Atlantic and the number of attacks which were actually being made by the Coastal Command planes. And he, from first principles, intuitively saw why this was the case. All the aircraft were painted black because they were used for bombing and night bombing. And this was believed, you painted the thing black, it would be the least easily seen. And of course, the answer was that the U-boats were seeing the Coastal Command aircraft and diving before the Coastal Command could detect them and make an attack. His answer was quite simple: paint all the aircraft white. And I remember the amazement of suddenly seeing white aircraft arrive on the establishment. This had an amazing effect on the U-boat attacks, and also a simple change in the setting of the depth charges made the captured German made the captured German U-boat commanders believe that a new weapon was being used. He was then, oh yes, another interesting and very brilliant thing. We were greatly troubled by the Focke-Wulf 200 aircraft bombing our shipping lanes west of Ireland. And Coastal Command only had 12 Beaufighters capable of dealing with these long-range German aircraft. And Blackett discovered that the commander of this force only thought that it was efficient to fly the Beaufighters when all dozen were serviceable. When now Blackett applied Poisson distribution, Poisson statistics to this problem, and of course he found out this was nonsense, and that you had the best chance of dealing with the enemy if you flew every aircraft whenever it was serviceable. That is a very good example of what we now call operational analysis was used by Blackett. After a year in Coastal Command, he went to the Admiralty and became the Director of Naval Operational Research, a post which he held until the end of the war. And it was in the Admiralty that he carried out, I suppose, his most difficult analysis, one of the most difficult pieces of analysis of the whole of his career. And this was how to obtain the most efficient protection of our merchant ships in the North Atlantic convoys. He discovered that there was a peculiar law of which nobody knew the origin. It was that the convoys should be small, and that the most efficient protection was to have a number of destroyer escorts according to the formula 3 plus n over 10, where n is the number of the ships in the convoy. Well now, Blackett, it was an extremely complicated analysis, as he recognized. It took him a long time, and his answer seemed to be that this was altogether wrong, and nobody knew the origin of this formula, and all the evidence that he was able to get together from the attacks on our convoys indicated that the convoys of large numbers of ships proportionally suffered the least losses. And it was from beginning in 1943, spring of 1943, that he persuaded the naval staff to increase the size of the convoys. Previously, there had been a limit that on no account must be more than 60 ships in a North Atlantic convoy. And Blackett, for as long as I remembered him, always had a feeling of acute remorse that he had not been able to arrive at this conclusion earlier. He estimated that if he had managed to reach this conclusion and persuaded the Admiralty to make convoys of great size, he would have saved 1 million tons of shipping in 1 year with large numbers of lives. Of course, he was not always right there. He had a bitter exchange with Slessor, who had succeeded Joubert as the C&C of Coastal Command. And this arose, I think, from the Tizard-Blackett antagonism to Charwell over the question of strategic bombing. And Blackett had wanted to switch 180 heavy bombers from Harris's Bomber Command to Slessor to use over the Bay of Biscay. It is rather odd that Blackett did not realize he launched this paper to the War Cabinet without recognizing that the tactics over the Bay of Biscay had suddenly changed dramatically because of the U-boats were being made to surface by day because of the use of a new form of centimetric radar. And this led to a very bitter exchange between Slessor and Blackett. And Slessor complained to the First Sea Lord that he did not want these bombers, and this was slide rule strategy of the worst kind. I think in the end, it's difficult to know who was right about that. I think that both Slessor and Blackett were partially right. Well, I will just come back to Blackett's activities in a moment, but he certainly, as the rector said, initiated what is now known as operational research in the most dramatic way in the three principal commands of World War II. However, he resigned as DNOR in 1945 and returned to Manchester, and with tremendous vigor restarted his cosmic ray research, extending the staff very largely. And as many of you will know, in 1947, it was his 10-ton magnet, which he'd brought from Birkbeck, which was used by Rochester and Butler in a modified form, and they made this famous discovery of the V particles. The 50th anniversary of that, in fact, has just been celebrated this autumn in Manchester. Blackett himself began work, lectured very frequently in those days. He did not do much more cosmic ray work himself. It was terribly encouraging and greatly excited by the discovery of the V particles and all the work that the rest of us were doing. In fact, his belief that there was something quite fundamental about the nature of the high energy spectrum of cosmic rays had an effect which eventually, by a complicated story, this is, and I cannot explain it now, but hope to describe it in more detail in the centenary celebrations here next April. This led directly to the beginnings of Jodrell Bank and to the erection of the Large Telescope, for which, of course, I do not think that there's any other person, any other scientist at that time who would have allowed that, not only allowed it to happen, but did his very, very best to make it happen. But I just make that remark now and hope to say a little more about the circumstances in the April celebrations. Blackett, he did a little work on the Cherenkov radiation. This started off a new investigation of the method of investigating the cosmic rays, and then a truly remarkable thing happened. He became interested in the effect of the solar magnetic field on cosmic rays, and during the course of his reading and work on this, he became interested in he saw reference to the work of Schuster on the angular momentum, the relation between the angular momentum and the magnetic moment of a rotating body. And I think this was in 1947 or 1948. Blackett discovered that there was a close proportionality between the ratio of the magnetic and angular moments of the Sun and the Earth. And just at that time, Chandrasekhar told him that Babcock had managed to measure the magnetic field of the star 78 Virginis. Well, Blackett was tremendously excited. He did a calculation of the rotation rate of the star and found that the relationship between the magnetic and angular moments held over a factor of something like 10 to the 10 to 1, and furthermore, that they were strictly proportional to the gravitational constant and velocity of light. And he thought he had discovered a new law of physics and a relation between the gravitation and magnetic fields. He read a paper to the Royal Society, and was so impatient at the delay in publishing it that he went to Brimble, who was then the editor of Nature, and had this paper published in a week. Well, of course, Runcorn, he sent Runcorn down deep mines in Lancashire, and Runcorn's measurements showed that this relationship was possibly not correct, and further measurements of Babcock, the relationship was not correct. I mean, it was just accidental that this relationship held. However, in the course of this work, Blackett became deeply interested in the general origin of the magnetic fields, and he then discovered that someone, I think in America, Department of Terrestrial Magnetism, had already attempted to detect the magnetic field of a spinning body, because according to Schuster and H.A. Wilson, anybody has a metal body, anybody has a magnetic field in its own right, independent of ferromagnetism or anything like that. And he proposed to, he built at Jodrell Bank, away from the disturbance of Manchester, he built a non-magnetic hut. And that hut is still there in beautiful condition, and no metal in it whatsoever. He proposed to spin a metal sphere at high speed near a galvanometer to detect this magnetic field of a rotating body. He had calculated from the previous work that no existing magnetometer was of sufficient sensitivity, and he had to achieve an increase in sensitivity of 1,000 or so times. And this led him to make this extraordinary magnetometer out of Alcanax magnets, in which in the end he could detect a magnetic field of something like 10 to the minus 10 Gauss. It was the most remarkable instrument, and it's a great memory to have been with Blackett when he was making this instrument and when he started using it. He borrowed some money to buy a 15 kilogram gold cylinder, which he thought that because of the differential motion of the cylinder of the Earth with respect to the magnetometer, it was too dangerous to spin it, that he would detect this magnetic field due to the presence of the gold sphere. Well, he did not succeed, and he recognized that the thesis was not correct, and the measurements of Runcorn and further measurements of Babcock had showed that this particular relationship, which had so excited him, was not correct. But typical of Blackett, he then, again during the course of this reading, came across this business of the magnetic properties of the rocks, and again, as the rector has said, this led to this historic work on the paleomatic field, and when he, in the middle of detecting the declination of certain sedimentary rocks, Triassic rock, sandstone rocks, he decided that the ones in Cheshire were originally near the equator. And at that time, he decided to come to Imperial College. I'm not going to say anything about his time at Imperial College because Mr. Barford is going to talk about that in a moment. I must say that Blackett wrote to me in 1953. He was in Italy, and I still remember the devastation when he said in his letter that he decided to accept this, to succeed G.P. Thompson in the chair at Imperial College. He said that he reminded me that he had never intended to spend more than 10 years in Manchester, and he thought that at his age, he was then in his 50s, was the last chance he had of starting another career. There were other reasons why he wanted to come to London, and I would just like to say a few words about that. He, of course, Tizard remained, though the influence of his committee disappeared, when Oliphant submitted the paper by Prowse and Frisch. When he submitted this to Tizard in 1940, Tizard set up the committee, which eventually became the Malt Committee, and of course, Blackett, being such a brilliant young man, was immediately a member of that committee. In fact, if you read Margaret Goring's book, you will find that he was the person who persuaded the committee that the bomb could not be made in this country by 1943 at a cost of £5 million. And according to Margaret Goring, it was Blackett's influence that led to the exchange with America and the creation of that. That is, by the way, because Blackett was still a member of that committee as the war ended. And in 1946, 1947, he fell completely foul of the Attlee administration. Some very well-known members, then the Anderson Committee, with Penny and Cockcroft and others on it, they all wanted Great Britain to proceed with the making of the bomb and get into the atomic energy business. Blackett strongly dissented. He saw Mr. Attlee on 2 occasions and wrote and submitted a memorandum to the inner circles of the cabinet. This memorandum was very badly received. The Foreign Minister Bevan wrote across it as rubbish. Attlee said the writer is a distinguished scientist, but a layman in military matters, and in fact, the Americans had just awarded him the Medal of Merit for his work on Operation of Work in the War. And the chiefs of staff said that they disagreed entirely and that his thesis was based on the assumption that the Soviet Union would be a friendly state. Well, Blackett resigned from this committee in 1947. He wrote Military and Political Consequences of Atomic Energy, this historic book, which was widely circulated. It was translated into many, many languages, and of course intensely annoyed the Americans. He held that the dropping of the atomic bomb on Hiroshima and Nagasaki was not the end of World War II, but the beginning of the Cold War. In fact, Blackett was very distraught at that time, and he did not like being excluded from the inner circles of authority. And in 1953, in the nadir of his political fortunes, was the time when he came to Imperial College. There is also another reason why he wanted to be in London then, apart from being a Londoner himself. In 1950, a person called Marcus Brumwell, a rather rich businessman, had convened a small group of distinguished scientists, Lochspizer, Zuckerman, Blackett, to work out a scientific and technological policy for Great Britain. They worked very closely with Gateskill and then with Wilson and Callaghan and so on. And the memoranda of these meetings, the minutes of these meetings I had them from Brumwell, and I believe they still exist in the John Rylands Library archive in the University of Manchester. But anyhow, Blackett was by Harold Wilson's side in this famous speech in Scarborough in 1963, when he referred to the white heat, the Britain that would be forged by the Labour government in the white heat of the technological revolution. In the Labour victory in 1964, the result of these deliberations we saw in the creation of the Ministry of Technology. Now, Mr. Wilson wanted Blackett to be a Minister of State in that ministry, but Blackett refused to go to the House of Lords, and he was made some other term, scientific advisor or chairman, something or other. But there is no doubt that those people I talked to who were associated with J.B. Adams, Morris Dean, Macfarlane, there's no doubt that Blackett, in fact, ran that ministry in the beginning as though he was the minister. However, the disillusion was very quickly arose. After a year in the ministry, Blackett wrote a memorandum expressing his dismay at the problems which they were not able to deal with. I think it was J.B. Adams who said that Blackett did not, although he tried to apply the methods of operational research which had been so successful during the war to a very complex labor relationship. And we had the disasters of the collapse of the Fairchild Company and all the troubles in Clydeside and the troubles with the unions. Well, it just happened, Mr. President of the Royal Society, that at that time I had the honour of being a member of council of the Royal Society, and the question of the successor to Lord Flory, who was then President of Rose, and everybody thought that Blackett should be made President of the Royal Society. And I was asked, but it was believed that his attachment to the Minister of Technology was so tight that he would not be willing to serve as President of the Royal Society. And since I was a member of council who knew Blackett very well, I was asked to have a private conversation with him. The result was extraordinary. I mean, Blackett said, there's one great wish to become President of the Royal Society. And I said, what about the ministry? He said, forget it. And in fact, he was elected in succession to Lord Flory, and his interest and work in the ministry rapidly declined. And I think when Wilson extended it to include the Ministry of Aviation, I think he resigned completely from the ministry. He did, of course, go to the House of Lords later in 1969. I think I'm going to leave Mr. Barford to talk to you about what happened when he came to Imperial College. There's just one other thing I want to say. That is that Blackett was often, and still is amongst people, thought to have been a communist. He was not a communist. He was a Fabian. He was extremely interested and very worried about the disparities between the rich and the poor. It seems to have originated in his Cambridge days. For a long time, his work and his attention and the differences between the rich and poor and his anxieties about the poor were related to this country. And then in 1947, he attended the first meeting of the Indian Congress of Science after the war, and I think it was next to Pandit Nehru, either to luncheon or dinner, and they immediately became great friends. Nehru asked Blackett about science in India and about the armed forces, and Nehru asked him to return to India. And Blackett very quickly became Nehru's scientific advisor, and particularly on the reorganization of the Indian Armed Forces. And he also set up the Magnetic Institute in the subcontinent, in Barber's Institute, which led to the paleomagnetic measurements in India. He was a frequent visitor to India. And if you read his speeches in the House, I think he only spoke 4 times in the House of Lords, and 3 of those speeches were entirely concerned with his anxiety about the underdeveloped countries, what should be done to them and what help this country could give to them. When I was asked to write the memoir for the Royal Society after his death, I naturally told Lady Blackett that I was going to do this. And I always remember what she said. Look, she said, you must write about India. She said, that person who wrote the obituary in the Times didn't even mention it. And in the end of his life, it was the only thing he cared about, the development of India and the poor countries. Well, I've used my time. It's been a very great pleasure to speak about Blackett. It's easy to say he was the greatest scientist of the century. In a century which contains Rutherford and so many other great people, one cannot say that. But he was unique in that he was a great scientist in nuclear physics, in cosmic ray physics, and in geophysics. He was also had a tremendous political influence in this country, and was a very great humanitarian. Thank you.
Well, ladies and gentlemen, it's a great pleasure and an honour for me to give this talk. and I'm very pleased to see so many old friends here, as well as people that I know were very closely connected with Blackett, but whom I've never met. Now, Tom's rather stolen my thunder at the beginning of this talk, because as a short talk, I didn't think it merited a long title. Nevertheless, I should complete, but it is only repeating what Tom has just said, bliss was it in that dawn to be alive. For I think that line, allowing for the poetic license, does encapsulate the impact that P.M.S. Blackett's arrival made upon this physics department. I must hasten to add that that's not to imply some similarity to the French Revolution, which is what Wordsworth was referring to. Although some faint hearts, when first encountering Blackett's commanding and rather severe presence, may have wondered, as he brought south his many Manchester colleagues, soon, inevitably, I'm afraid, to be christened the Manchester Mafia by the locals, I wonder whether those faint hearts may have wondered whether the tumbrils would follow. But it was, of course, the infusion of new blood rather than the shedding of old which characterised that dawn. That it should have happened at all arose from an extraordinary coincidence of fortunes of war, national trends, preferments, unexpected deaths, and powerful personalities. Although in 1935 the college had, in the Tizard plan, formulated ideas for expansion within South Kensington, these had long lain dormant. No large-scale study had been carried out or agreed during the pre-war period of economic stagnation. None could have been expected during the Second World War. That apart, the area on which most of the college now stands, the so-called island site, was shared during the 1940s with no fewer than 9 other institutions: the Imperial Institute, the University of London, the Royal College of Art, the Royal College of Music, the Royal School of Needlework, the Imperial War Museum, the Warburg Institute, the Science Museum, and the Institut Français, as well as several residences and the Alexandra House apartments. It must have been a daunting prospect to ease out so many tenants, so heavily loaded with royal and imperial pedigrees. However, early in 1950, the Attlee government did approve, via the University Grants Committee, a proposal for a major nationwide expansion in education and technology, to be led by doubling the size of the college. Again, economic problems and a change of government caused delay. Only at the very end of 1952 was government approval confirmed, now sufficiently definite for the college to embark upon serious detailed plans for expansion within the island site. 1953 was a crucial year for the physics department. The year before, Sir George Thomson, head of department since 1930, and nearing the end of his career as an active physicist, had resigned. It was doubtful whether he would have been happy organising the rapid growth of a department entering the post-war era of diverse big physics. More so when, as it turned out, this would have involved supervising the design of a large new building. Such problems had been shed when he became Master of Corpus Christi College and moved to Cambridge. After a short interregnum, P.M.S. Blackett arrived to take charge of the expansion of the department in both scientific and building terms. At that time, the college, with Sir Roderick Hill as rector, was basing its proposed expansion on 2 master plans prepared by the architects Norman and Dorbarn. Both envisaged rebuilding the island site to a design of grand symmetry, with a line of science buildings stretching along Queen's Gate, balanced by a similarly shaped line of engineering departments along Exhibition Road. However, the only cleared area then available was a bombed site in the northwest corner here. Thus, the first possessor of a complete new building would be a physics department. The Royal College of Science building on the south side of what is now named Imperial College Road had housed physics and chemistry since 1906. It had a handsome facade, but its interior was ill-suited to accommodate the teaching and research envisaged for the second half of the 20th century. Physics and chemistry were thus clearly rivals for the new building. It would be interesting to know just what had been promised to Blackett by Sir Roderick Hill, for the latter died unexpectedly not long after Blackett's arrival, and Patrick Linstead, head of the chemistry department, succeeded him as rector. Had the new building already been allotted to Blackett as an inducement by Sir Roderick, or did the two powerful Patricks fight it out later? I'm much indebted to Anne Barrett for help with the college archives, but this matter so far has evaded her and remains speculative. I do just wonder whether the rector has a store of secret files bequeathed by his predecessors, not to be opened for 40 years perhaps, which he might let us have a peep at. In the event, physics had the advantage, though few then thought that the less fortunate would have to wait so long to be rehoused. Blackett exploited this good fortune to the full, establishing new chairs and bringing in new staff to set up new lines of research. Though joining a department with him at its head was undoubtedly the main attraction, it is also true that an additional incentive was the prospect of moving from laboratories which throughout Britain were looking a little tired to spacious new accommodation, accompanied by funding on a scale not known until then and rarely experienced since. As Blackett himself wrote, I did not wholly relish spending a good part of my relatively few remaining years as an active scientist in coping with the planning and supervision of such a complex building. Now, one of his outstanding qualities was his willingness to delegate, without interference, important responsibilities to his junior colleagues, but also to back them fully with his own considerable authority when the going got tough. When he asked Bill Thompson, the departmental superintendent, Brian Coles, and me to take part in preparing the department's brief for the architects and to act as liaison with them, I did not then anticipate how necessary and valuable that support would be. With building concerns thus delegated, he set in train radical changes in the range and scale of the department's research. At the time of his arrival, there were only two groups sufficiently well established to have separate teaching as well as research programs of their own: technical optics under Professor Wright and geophysics led by J.M. Bruckshaw as reader. The nuclear physics group, centred around two Van de Graaff generators, also had a professor, Sam Devons, but was regarded rather as part of the physics department proper, as were those engaged in the other research activities at the time, such as spectroscopy, cosmic rays, electron diffraction, thermonuclear processes, and acoustics. Pioneering work at Bristol and Manchester had opened up a whole new field of subnuclear particles using nuclear emulsions and cloud chambers to study cosmic rays. And for some time, both techniques were employed here. However, it was only the advent of bubble chambers and allied scanning devices that made possible the analysis of the large number of photographs from Earth-bound accelerators. And a very large group with Clifford Butler at its head then concentrated upon particle research. After various changes of name, this work is now, of course, called high-energy physics. The fast space aspect of cosmic rays continued as a separate field of research when Harry Ellett also followed Blackett from Manchester. Here too, names change with time, and astrophysics is the current successor. However, it was the establishment of quite new groups, as well as the enlargement of the old, given the status of sub-departments, and accorded considerable autonomy under a professor or reader, that made the big break with tradition. Thus, J.D. McGee was brought in from EMI as Professor of Instrument Technology, the first of a series of new chairs that was to change the whole structure of the physics department and would lead eventually to the practice of a rotating head of department. Large departments of the college were traditionally headed by the professor. And although there were some other junior professors, the professor, was the department and characterised his department until he departed. Not much thought then that it might just be her and she. They were known collectively and affectionately or otherwise as the robber barons. Undoubtedly, it continued to be the case that while he remained head, Blackett did characterise the department. It must be admitted that Blackett himself could don the mantle of robber baron at times. He did, after all, prize Abdus Salam and his group from the mathematics department and set them up in brand new offices in level 5 above. But that, of course, was in a good cause. As a result, this building could soon boast of housing, in proper style, 2 Nobel laureates. More seriously, though, this was part of Blackett's conviction that experimental and theoretical physics must not be separated, and at least share the same building and the same common room. Since he started this policy, there has, of course, been much further strengthening of theoretical work, as we have seen, for example, with the group set up alongside astrophysics and experimental solid-state physics. Such initiatives could only have been founded on the creation of new posts at all levels. What were then tenured academic staff more than doubled during his 10 years as head of department. And supporting staff, technical and secretarial, grew likewise. Undergraduate numbers grew from around 140 to nearly 350. However, the most dramatic rise was in the number of postgraduates, from around 20 to over 100. A major part of this came from the great increase in the number of research assistants, an innovation that not only gave a great fillip to the research output, but was later to form an integral part of the undergraduate tutorial system. Sir Bernard referred to the fact that many of the things that Blackett started carried on long after him. Here in particular was an example of how his influence at that time made big differences later. Now, it is remarkable in the midst of these great enterprises that Blackett found time to continue any research activity himself. Sir Bernard has mentioned this already. Blackett was determined that his ingenious but idle magnetometer should be put to good use. So John Clegg and Peter Stubbs were dispatched abroad to bring back rock samples for it to measure. The contribution this work made to the theory of continental drift and questions concerning reversals of the Earth's magnetic field could hardly have been better as justification of that determination. Matters had already been referred to. Now, I spoke earlier of Blackett's quality of support for junior colleagues, so let me return to this building, for it was during its planning and that twice at first hand I benefited from it. Practice was for architects to prepare by themselves their responses to the client's brief. If the client wasn't satisfied, a second set of plans would be drawn up and commented upon, and so on. An iterative process that was supposed to converge to a happy solution. Now, we all know that such iterative processes do not necessarily converge. They may oscillate wildly, even diverge to an exponential disaster, as seemed to threaten in this case. The second problem arose from the overall college master plans. In these, the main pedestrian entrance was to be an exhibition road in the east, and this was to carry on as the principal walkway, feeding all the departments throughout the site, until it reached us in the far northwest corner here, considerably above ground level. Now, this left us with a rather insignificant door and a modest flight of stairs as the only direct entrance, indeed the only entrance for many years to come. I will well remember Blackett describing it witheringly as the back entrance to the college. It was clearly time for a Blackett intervention. Now, in these two matters, architect-client protocol and planning priorities, the senior architect, Graham Dorbaum, appears in my memory to symbolise the immovable object, while P.M.S. Blackett has the role of the irresistible force. Now, we all know that the conundrum about what happens when these two meet is self-contradictory and nonsensical. But let us throw logic aside. I must tell you, on the statistical basis of 2, that it is the irresistible force that wins. We thus soon reached amicable agreement over the planning of the whole building, when it was agreed that I should thenceforth trade ideas to and fro with the site architects over the drawing board. And as a result, our architects proceeded to provide us with a building of quality, I think still unequalled throughout the site. And it was one in which we gained a much more fitting entrance, flanked by this fine theatre and the departmental library on either side. I should like to finish by going back to Wordsworth. The poem containing the line I quoted is a rhapsodic account of high expectation, that a wide range of thought and talent were joined together to achieve a heaven upon earth. Sadly for Wordsworth, these expectations had largely vanished 10 years from that dawn, but in our case, the result was quite the reverse. 10 years from Blackett's arrival, those of us working here and enjoy the privilege of experiencing great hopes fulfilled. We had seen a renaissance at first hand, and a status and reputation firmly established for the physics department that continues to this day. This building already bears his name. Among the equations and diagrams carved by John Skeeping above the entrance, which survey our knowledge of physics up to around the mid-1950s, it has one derived from Blackett's own cloud chamber photographs. How fitting it is that the building will now also have the Epstein bust to remind us so vividly of Blackett the man. Thank you.
Well, thank you. It's a great honor to be here this evening, celebrating the 100th anniversary of the birth of P.M.S. Blackett. I can't add much to what you've heard from Sir Bernard Lovell and Norman Bamford, but I shall speak from the point of view of one of his successors at the Royal Society. I did not know Blackett, but I did meet him on 2 occasions. One, when I was admitted to the Royal Society, he was then president, in 1969, and in 1970, when he opened a discussion meeting organized by a colleague and myself. I remember well the lean, handsome figure, the sharp, questioning intellect, and a powerful personality still evident in a man in his 70s. In fact, he took a special interest in discussion meetings. They had been introduced only recently in the form of 2-day international symposia on major fields of scientific research. The papers were published in the Transactions of the Society, leading to authoritative volumes with a worldwide circulation. Blackett did much to build up the importance and prestige of these meetings, not just because of the science, but because of the international character of these meetings, which drew people from all over the world. Indeed, Blackett had set out as one of his, actually the first of his 5 aims for the Royal Society when he became president, the promotion of international science, particularly in relation to Europe. Before the 1960s, the Royal Society was something of a club in which, at occasional and usually ill-attended Thursday afternoon meetings, short scientific papers were read, and after that the fellows dined at the Royal Society Club. I haven't been able to pinpoint the exact date at which these meetings came to an end. It was certainly in Blackett's time. He certainly, from all I've heard, had no patience with them, and they were replaced by the discussion meetings which took place on a Thursday, beginning sometimes the day before. As you have heard from Sir Bernard, Blackett regarded his election as president in November 1965 to the Royal Society as the climax of his career. Before that, he'd been heavily involved with the Labour Party, particularly after Harold Wilson succeeded to the leadership of the party in 1963. And Blackett's influence is detectable in Wilson's words on the white heat of the technological revolution, in which, and I quote, "There will be no place for restrictive practices or out-of-date methods on either side of industry." Blackett, of course, advocated this because he was very conscious of the obsolescence of much of a country's industry and the complacency with which it was accepted, perhaps, as I think he thought, as a relic of the past wealth from the empire which had rather concealed it. But with the advent of the Labour government in 1964, Blackett became an influential figure in British politics and in science policy, as you heard from Sir Bernard. This led to rather large changes in the administration of scientific research. The old Advisory Council on Scientific Policy was abolished, and on Blackett's advice, technology was separated from science in the new Ministry of Technology, of which we've just heard. He was the ghost minister, while a new Council for Scientific Policy was set up under the Department of Education and Science. This was, I think, an unfortunate division. Apart from recommending the pattern of division of available resources between the various research councils, this new body, the Council for Scientific Policy, had very little to do, coexisting as it did with the Ministry of Technology, which had its own advisory council, and the newly created post of Chief Scientific Advisor in the Cabinet. This post was, of course, held by Blackett. Blackett was Chief Scientific Advisor to the government at the same time as President of the Royal Society, something which wouldn't happen today. According to Blackett's successor as President, Lord Todd, the independence of the Society was in some measure affected by Blackett's political commitment to the Labour government. Whether this was true or not, I cannot tell, but even if one might not have agreed with all that Blackett did in this sphere, he certainly woke up the British science establishment. This active intervention of Blackett's was a sharp change for the Royal Society, which from 1950 to 1965, under 3 successive presidents, had drifted away from matters of public policy. In Lord Todd's words, the Society had become introspective, being concerned with internal matters, its centenary, its premises, and so on, and had gradually lost the influence that it had earlier. When in the days of the Advisory Council of Scientific Policy, it was represented ex officio on the committee. However, Blackett's activities seem to have had a direct influence on his successor, Lord Todd, despite Todd's remarks, because under Todd there was ushered in a new phase in the Society, in which specific appointments were made within the Society to reinforce its ability to give advice proactively to the government. In preparation for this ceremony today, I've been reading Blackett's annual addresses to the Royal Society. It is striking how some of the themes, some of the issues he touched on could have been repeated almost to the word today. We hear of his concern that engineers and technologists in Britain do not receive the public esteem which their ability and importance to the community would justify. He was convinced that the rate of growth of the science budget should remain high for a long time. But at the same time, the grant-giving bodies who had the task of selecting the best projects should apply strict selectivity. I quote, "Only by rather rigorous selectivity can a relatively small country like Britain hope to reach the world front line of advance in many fields and remain there." But however much Blackett did for British science, and he certainly did his duty, he'll be longer remembered as a scientist, as the man who, with his improved Wilson cloud chamber, first photographed in nuclear transmutation, and again, nearly 9 years later, together with Occhialini, photographed with their new counter-controlled cloud chamber the production of electron-positron pairs, and moreover, understood what he actually saw. He had been talking to Dirac, much apparently to the disdain of Rutherford, who thought it rather a bad show that the theory had preceded the experiment. They were difficult experiments, and it was Blackett's gift for design of apparatus and his engineering skill which led them to succeed. I'll finish by letting the naval officer, the practical man, have the last word. He is here speaking of the Geiger counter. In order to make it work, you've had to spit on it, on the wire, on some Friday evening in Lent. Well, I've been asked to unveil the bust by Epstein of Patrick Blackett. Now, it's quite a difficult job to unveil a bust which was already up on the wall. And so I'm going to do a meta-unveiling. That is, unveil a plaque which commemorates the unveiling of the bust. Now, I think it's a magnificent head. I had seen it before. It's very characteristic of Epstein, and I imagine very characteristic of Blackett. It certainly brings out the memories I have of him, because I had heard him lecture and speak. And so it gives me great pleasure to unveil his bust, looking out upon the building which he created, as you just heard from Norman Barford, and I will simply do it.